Hello everyone, welcome to class 3, lecture 3 of the second week. In this lecture, we will explore Cauchy sequences, examples of Cauchy sequences, then some of the theorems like every Cauchy sequence is convergence sequence, and then we will prove that Cauchy general principle of convergence theorem. That will be the lecture layout. So, as I told you that in this lecture we will cover Cauchy sequence, some basic theorem and Cauchy general principle of convergence and examples as well. So, what is Cauchy sequence? It is a peculiar sequences where you will see that after some terms the adjacent two terms are closing each other arbitrarily, and closes so much that it's ultimately converges to some points, right. So, mathematically a sequence an of real numbers is called Cauchy sequence if for any given epsilon greater than 0 there exists a natural number p, obviously depending on epsilon, such that the two terms an minus a modulus, that means the distance between the two terms an and am is arbitrarily close to epsilon. So, it is less than epsilon for every nm greater than or equal to p. So, let me explore this for you geometrically. So, here let us say we have different terms of the sequences, and let us say we have here a p as a natural number n. So, that means here we have a p, right, sequence terms. After that, choose any two, not arbitrarily adjacent to this one, but you can choose like this term and this term as well. If these terms, let us say naming as an minus am, the distance between these terms is going to be less than the given epsilon by which p has been evaluated. If it happens for every nm, not only these two fixed n or m, but any nm after this p, then such a sequence is a peculiar sequence and we call it a Cauchy sequences. Another definition for in a different way, and in a minute you will see that it is also going to be proved by the basic definitions. So, a sequence an is said to be Cauchy sequence if for a given epsilon greater than 0 there exists a positive integer m such that an plus p minus an modulus is less than epsilon for every n is greater than or equal to m and p is nothing but 1, 2, 3, 4, 5 and so on. So, here in the first example we have p as a natural number. In the second definition we have m as a positive integer and as well as only one n is greater than or equal to m. Whereas in the first one we have chosen the two terms n and m such that for every nm greater than or equal to p, after that p each term is arbitrarily close to each other. Now, what I have already told you that every Cauchy sequence of real number is bounded. So, let n be a Cauchy sequence of real numbers and we need to prove that this sequence is going to be bounded. So, for a time being and for simplicity, let us choose epsilon equal to 1. Here we have chosen, and then there exists positive integer k such that the difference between the two number an and am is going to be less than epsilon. Here epsilon is equal to 1, so it is less than 1 for every mn is greater than or equal to k. So, that means we will use the inequality. What is the inequality? Inequality is modulus of an minus modulus of an is always less than or equal to modulus of an minus am, and it is given right in the previous one, the first one. So, it is less than 1, which is less than epsilon, that is right. So, that means modulus of n can be written as 1 plus of modulus of m for every mn is greater than or equal to k. Now, put m equal to k. So, here in the right hand side put m equal to k. So, what happens? Modulus of n is less than or equal to 1 plus modulus of ak, and this will happens for every n is greater than or equal to k. You have already here seen here, right. So, every n is greater than or equal to k. So, we have a sequence an which is less than 1 plus of modulus ak, and this happens for every n after some terminating term k. So, choosing maximum capital M as a maximum of modulus of a1, modulus of a2 and so on, modulus of ak minus 1, 1 plus of modulus of ak. then modulus of an is less than or equal to capital M. Here this is the maximum. So, this is the less than or equal to capital M as well for every n which belongs to natural number. Thus, there exists a real number M such that each term of that sequence, modulus of that terms of that sequence is less than some real number, given real number capital M, and henceforth this is the definition of a bounded sequence. So, that's we have proved that Cauchy sequence is a bounded sequence. Now, we will prove the Cauchy general principle of convergence. A necessary and sufficient condition for the convergence of a sequence an is that for every epsilon is greater than 0, there exists a positive integer m, natural number m, such that an plus p minus an modulus is less than epsilon for every n is greater than and equal to m and p is equal to 1, 2, 3, 4, that means natural number. Or in other words, we call it necessary and sufficient condition for a real sequence to be convergent is that it is a Cauchy sequence. So, if you have a Cauchy sequence, it is a converging sequence. If you have a converging sequence, it is a Cauchy sequence. That is what we have a necessary and sufficient condition. Let us prove the first necessary condition. The condition is necessary. That means every convergence sequence is going to be a Cauchy sequence. It is very easy to prove that, right? So, remember that one, what will be the definition of a convergence sequence. So, for a convergence sequence, we have already seen that for any arbitrary epsilon greater than 0, there exists some natural number, right? And by which you have an minus of that converging point or the limit L modulus is less than epsilon for each n greater than and equal to that natural number, right? So, we are going to use the same definition for this converging sequence, and using that sequence we will find out that it will be a Cauchy sequence. So, for an be a convergence sequence, that means for simplicity let us suppose that it converges to a real number L. Then by definition we have an minus L modulus is less than epsilon by 2, and since an minus L modulus is less than epsilon by 2, I can write down an plus p minus L is also less than epsilon by 2, isn't it? Because n is also a term of that sequence and n plus p is also a term of that sequence. So, I can write these two things, and now we can calculate an minus an plus p, and what it will happen, an minus L, we can add and subtract L by both. So, n minus L plus of L minus n plus p modulus, and these whole modulus is less than sum of the individual of these terms. So, n minus L modulus plus of L minus n plus p, right? And it is given, right? N minus L modulus is less than epsilon by 2 and n plus p minus L modulus is less than epsilon by 2. Henceforth, the whole term n minus n plus p modulus is less than epsilon, and that is the definition of a Cauchy sequence. So, it is a Cauchy sequence. Now, we will going to prove the sufficient condition, that is every Cauchy sequence is a convergent sequence. So, for that let n be a Cauchy sequence of real numbers, then n is a bounded sequence, and hence by Bolzano-Weierstrass theorem it has a limit point, right? Now, say it is L. Now, so that sequence n converges to L, that is our motive. So, for every epsilon is greater than 0, since n is a Cauchy sequence, we can write this one, the arbitrary close two terms are going to be closed, and we can write this one n minus am modulus is less than epsilon for every n is greater than or equal to m, right? That is the definition of the Cauchy sequence. So, since L is the limit point, there have infinitely many points of n in the neighborhood of L. We have already seen this, right? L minus epsilon is less than n is less than L plus epsilon, then L is the limit point of this sequence an, right? We have seen this. So, this is the epsilon neighborhood of L, right? So, that is what we are talking about, that infinitely many terms of n must be lying in the neighborhood of L. Hence, for the above choice of epsilon and m, there exists a positive integer k greater than m such that a k minus L is less than epsilon, and since k is greater than m, therefore, from 1 we have a k minus am less than epsilon. Now, you can see here 1 is an minus am. So, we have to replace this one a k minus am, right. So, we have chosen in such a way that it comes out a k minus am is less than epsilon. Now remember these three, 1, 2 and 3, and using these three we can calculate here an minus L, because we have to show that this sequence is converging to a limit point L, right? So we are going to find out the differences between the sequence term an minus of this limit point L. So it can be written as an minus am plus am minus ak plus ak minus L. So I have adding and subtracting am as well as ak in itself, right? Adding and subtracting both these two terms, then you will find out that the whole modulus is going to be less than or equal to individual of these terms, these three terms. So this will comes out these three individuals, and each one is given. This is from 1, so this is less than epsilon. This is from the second, so am minus ak is less than epsilon. Ak minus L is the third one, so it is less than epsilon. So using 1, 2, 3, we will find out that an minus L modulus is less than 3 epsilon, not epsilon, and this can be renamed as a epsilon dash. So that means we have an minus L modulus is less than epsilon dash for every n is greater than and equal to m, and henceforth sequence an converges to the limit point L. Hence every Cauchy sequence of real number is a convergence sequence. This is the Cauchy general principle of convergence, and we are going to use it to show that a sequence is converging, and if it is converging, then it may be a Cauchy sequence, and it is a Cauchy sequence, right? So now look at in the problems, and I will provide you the solutions here. So that the sequence an equal to 1 beta n is a Cauchy sequence, and hence it is a convergence sequence. So our target is to prove that it is a Cauchy sequence, or directly it is a converging sequence, right? For a convergence 1 beta n, we have already done a lots of time, where we have seen that this sequence is nothing but this sequence is already converging, and it's converging to a point 0, which is not a sequence term outside of the sequence, right? We have already seen this one. But how to prove that this is a Cauchy sequence? So we are going to use this Cauchy general principle of convergence to show that it is a converging sequence. So for n is greater than m, we are going to calculate modulus of an minus am. What will be the value? An has the value 1 beta n, and am has the value 1 beta m. Take the determinant, LCM of the determinant. So it will comes out n minus m divided by mn. Now choose 1. So I will choose n. So this, the whole term here, n minus m divided by mn, must be less than n divided by mn, isn't it? So why? Because it has already minus of am. That's why it is a bigger term. This is a bigger term, n divided by mn. And also this will gives you 1 beta m. So that means an minus am is less than equal to 1 beta m. So if I choose epsilon in such a way that it is epsilon is greater than 1 beta m, right? Then if epsilon is greater than 0, then by taking m, that means this will gives you m is greater than 1 beta epsilon. So if I choose a natural number m such that 1 beta m it is greater than 1 by epsilon, then we will find out that m is greater than 1 by epsilon will fulfill our criteria of the converging or Cauchy sequences. An minus am is less than epsilon for every n is greater than m, and henceforth this is a Cauchy sequence, and every Cauchy sequence is a converging sequence by Cauchy general principle of convergence. Henceforth it is a convergence sequence. Similarly, can we show that an, that is minus 1 by power n is not a convergence sequence? So look at the terms first. So this is the term of this sequence. This is an alternating type of alternating each term. So minus 1 1 minus 1 1 and repeating it, right? So that means it's an oscillatory sequence. So the sequence can be, look at this term by this one. So here it is 1, this is 1, this is 1, this is 1, this is 1, and this is 1, something like this, right? So this is an oscillatory type of the sequence. So taking epsilon 1 by 2 and calculating n plus 1 minus n, that will gives you minus 1 per power n plus 1 minus 1 per power n, that is equal to 2, right? Modulus of this is 2, and which is obviously not less than epsilon, which is not less than epsilon. If I take epsilon equal to 1 by 2 epsilon or something 1 by 4, 1, 1 by 5 and so on, whatever the less than 2 will not work here. So that's why, and we have already told that for any given epsilon, so epsilon is arbitrary. Here we have taken one value epsilon equal to 1 by 2, and that inequality does not satisfy, and henceforth this sequence is not a Cauchy sequence, and henceforth the sequence is not a converging sequence as well. So that the sequence a n equal to 2 pi power n is a converging or converging sequence. So now calculate for a given epsilon is greater than 0. Now calculate the differences between two terms a n minus a m modulus. This will comes out to be 1 by 2 pi power m into 1 by 2 pi power n minus m minus 1, right? And obviously it is less than 1 by 2 pi power m, isn't it? So this is less than 1 by 2 pi power m because it's a positive number or non-negative number. It's a modulus. It is in the modulus. Henceforth, it is less than 1 by 2 pi power m, right? So therefore, it is less than epsilon implies 1 by 2 pi power m is less than epsilon, and since this is less than 1, we have calculated this one, right? So this will gives you 2 pi power m is greater than 1 by epsilon, and it is only happen if m take the log both sides. So m log 2 is greater than log 1 by epsilon. So it will gives me m, the value of m which is greater than log 1 by epsilon 2 divided by log 2. So if I choose a positive integer or natural number m such that it is greater than log 1 by epsilon by log by 2, then this will be happen a n minus a m is less than epsilon for every n is greater than or equal to m, and that means it is a converging sequence, converges to where? So by using the Cauchy general principle of convergence, it is a converging sequence. So that with the help of Cauchy general principle of convergence, that the sequence a n where a n is given, right? So a n is given 1 plus 1 by 2 plus 1 by 3 plus 1 by n is not a convergent sequence, right? So one way to show that you have to calculate this first, 1 plus 1 by 2, 1 by 3 and so on, and expand the whole sequences. So this is the sequence. So you have to find out the summation of this 1 beta n from where to where, from this number n from r equal to 1 to n, right? So this is one way to prove this one. That is, you have to firstly calculate a n, and then by this a n you have to expand the whole sequence and look at the differences between these two numbers, if they are arbitrarily close or not. If they are arbitrarily close, that means it is a converging sequence. If they are not, then it is going to be far away to each other and it's going to be divergent, right, or not converging. So, but look at the principle we have already proved in the earlier slides. So, suppose a n is a converging sequence. For time being, let us suppose that a n is a converging sequence. Then for epsilon equal to 1 by 4, why I have chosen this a specific term? It is not a fixed one, but since I want to prove that if I choose epsilon equal to 1 by 4, the theorem is not valid. That is why I have chosen here. You can choose anything, it does not matter. You just slightly adjust to each other and it will gives you the same thing. There exists a positive number n is greater than or equal to m and p is greater than or equal to 1 such that a n plus b minus a n is equal to 1 beta n plus 1, 1 beta n plus 2 till 1 beta n plus p. So how I have written this one? So you can see here 1 beta n plus p is equal to what? 1 plus 1 by 2 plus so on, plus of 1 beta n plus of 1 beta n plus 1 plus of 1 beta n plus 2 and so on till 1 beta n plus p, right? And what is the a n? A n equal to 1 plus 1 by 2 plus 1 by 3 and so on till 1 beta n. So now take the difference of these two. So take the difference, 1 is cancelled out, 1 by 2 is cancelled out and so on till 1 beta n. So what remains? It remains 1 beta n plus 1 plus 1 beta n plus 2 plus of so on till 1 beta n plus p here, right? And we have already chosen that this is less than epsilon. That means it is less than 1 beta 4. Now in particular, if I put n equal to m, we have 1 beta m plus 1 until 1 beta m plus p, which is less than epsilon, which is less than 1 beta 4, right? So now taking p equal to m, we see that m in place of p we have m plus m, so it is it's coming out m divided by m plus how many terms we have, 1 2 3 and so on, how many, p. So this is the p terms, right? 1 2 3 and so p terms. So p equal to m will give you m terms, so m divided by m plus m, so this will comes out to be 1 by 2, and these terms are the bigger than by m, because I have chosen 1 beta m plus 1 plus of 1 by m plus 2, replacing this 1 by m, replacing this 1 by, so making the whole each term, denominator of each term is equal to m plus m. So that means bigger of this, so the left hand side must be greater than the right hand side. And how many terms we have? We have m terms. So what will get that? That will gives you m divided by 2m. So mm cancel out and you will have a 1 by 2. And now we have already chosen that it is less than 1 by 4, which is not the case, right? So that's why I have chosen 1 by 4. You can choose 1 by 6, 1 by 7, 1 by 8. Any number which is less than 1 by 2 is going to be fulfill our purpose. And this is a contradiction, since 1 by 2 is not less than 1 by 4, henceforth this sequence is not convergent. If it is convergent, it has to be fulfill the same things, right? Now look at the problem number 5, where we have a Cauchy general principle of convergence. Using the Cauchy general principle of convergence, we have to show that n square is not a convergent sequence. One way, without, if it is not given that Cauchy general principle of convergence, then we can have this sequence like 1, this is 4, this is 9, this is 16, this is 25 and so on. And look at this sequence, it's not converging, it's the diverges to plus infinity, right? That is quite easy to see that. But how to prove this one? By using the Cauchy general principle of convergence. So suppose n is given, n is equal to n square, then am is equal to m square. Now take the differences between these two. So n minus am modulus is less than n square is equal to n square minus m square, and use this like a square minus b square. So n minus m into n plus 1 for every n is greater than m. So that is greater than n plus m, right? And which is greater than 1, because n is a natural number, m is a natural number, therefore n plus m must be greater than 1, strictly greater than 1. n starting with 1 2 3 4 5 whatever it is, and m is also 1 2 3 4 5 6, and n is greater than m, right? So n plus m must be greater than strictly 1. So taking again epsilon which is less than 1, it will show that n minus m is less than that number. I have chosen here for 1 by 2. You can choose 1 by 3, 1 by 4, 1 by 5, whatever it is. So this will show that the sequence is not a Cauchy sequence, and hence we cannot have any m such that for n is greater than m, it's fulfill n minus m modulus is less than epsilon. No, we cannot have any m. So there does not exist any m natural number such that it will happen. So that's why it's not a converging sequence, it is a diverging sequence. Now this is the last problem I have chosen for you. So this is the question number 6, and it says that so that with the help of a Cauchy general principle of convergence of a sequence, the sequence 1 by root n is convergent. So again we will do for chosen or given any epsilon greater than 0, there exists a positive integer m such that n minus ap is less than epsilon for all np is greater than or equal to m. So assume without loss of generality that n is greater than p. Then n minus p is 1 by root n minus 1 by root p, and this will calculation will give you root p minus root n divided by root np ka modulus. So this will comes out to be root np minus root p into root np minus root p divided by this. So I have multiply in the numerator and denominator by root n plus root p, right? We can do this. So the the above one will give you n minus p, and the denominator will give you root n plus root p into root np, and then take the minimum of NP is greater than M, and this will comes out to be this is if I take this one, then it will comes out 1 by root M. So I can write this one as An minus AP modulus is less than some number which is less than 1 by root M. So accordingly we can choose M in terms of the epsilon. So if I choose M is greater than 1 by epsilon, that means natural number M such that it is greater than 1 by epsilon square, then for all NP is greater than or equal to M, this will satisfy our equations. Modulus of N minus AP is less than epsilon. This shows that this is a Cauchy sequence, and moreover by general principle of convergence it is a converging sequence. And how it converges? 1 by root n converges to 0, therefore it's the limit is 0. So it is a Cauchy sequence and converging to 0. So thank you so much.